Hi dear students, today we talk about the last topic in the unit, that is the Helmholtz Theorem. Actually, the laws of electricity and magnetism have been expressed in terms of the electric and magnetic field as differential equations. That is, we have the four equations that you will learn in the next chapters. That is, first equation del dot E, that will be equal to rho by epsilon 0. Del dot B is equal to 0. Curl of E equal to minus rho B by dot T. Curl of B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dot T. All these are the differential equations of the fields E and B. Okay. And to find out this electric field or the magnetic field, we have to solve this differential equation. Solving these differential equations and hence to find out the vector function E and B, we need boundary condition. What is that boundary condition? For example, the electric field. The expression for the electric field you might have learned in the plus 2 class. That is 1 by 4 pi epsilon 0 q by r square. This is the electric field of a point charge. As moving away from the charge, particular point P, the electric field is given by this expression. Here the boundary condition, we can say that when r tends to infinity, this electric field is proportional to 1 by r square. That means that will be 1 by infinity square, that will goes to 0. The electric field vanishes far away from the point charge Q. This is the boundary condition. To find out this electric and magnetic field, we have to solve this differential equation and we have to apply the boundary condition. അപ്പോൾ ഇവിടെയാണ് ഹെൽമോൾട്ട്സ് വേറൊരു വഴി പറഞ്ഞിരുന്നത്. അതായത് if the boundary conditions of a vector function is given, then that vector function is uniquely determined by its divergence and curl. The statement of the Helmholtz theorem is this one. If the boundary condition for a vector function is given, then that vector function is uniquely determined by its divergence and curl. Okay, let me take that f is that vector function. F is a vector function that is to be determined. We don't know what is this f, exact form of this f. This f may be the electric field or magnetic field in a particular case. Okay, then the divergence of that f is given. Del dot f, the divergence of that is d. D is a scalar function. Of course, divergence of any vector is a scalar. The curl of that vector function is given. Del cross f is also given. The curl of this vector function is c, where c is a vector function. Because curl of any vector is a vector. Fine. Then we have learned an identity, that is, we know the divergence of a, we know that the divergence of curl of any vector is is 0. If I write here divergence of curl of any vector, divergence of curl of any vector means divergence of curl of any vector del cross f, that is equal to 0, then this del cross f curl of S is nothing but our C, because we have chosen like this. That is del dot C is equal to 0. അതായത് ഹെൽമോൾട്ട്സ് തിയറം പറയുന്നത് any vector function f that can be uniquely determined if its divergence and its curls are given. ഇപ്പോൾ ഒരു വെക്റ്റർ ഫംഗ്ഷൻ്റെ ഡൈവേർജൻസും കേളും തന്നിട്ടുണ്ടെങ്കിൽ, ബൗണ്ടറി കണ്ടീഷനും തന്നിട്ടുണ്ടെങ്കിൽ, നമുക്ക് ആ വെക്റ്റർ ഫംഗ്ഷൻ എഫ് എന്താണെന്ന് കണ്ടുപിടിക്കാൻ പറ്റുമെന്നാണ് നമ്മുടെ ഹെൽമോൾട്ട്സ് തിയറം പറയുന്നത്. ഇതുമായി ബന്ധപ്പെട്ടിട്ട് രണ്ട് പൊട്ടൻഷ്യൽസ്, ഇപ്പോൾ കണ്ടീഷൻസ് ഇങ്ങനെയാണെങ്കിൽ വാട്ട് വിൽ ബി ദ പൊട്ടൻഷ്യൽസ്, അതാണ് നമുക്ക് ഇനി പറയാൻ പോകുന്നത്. Potentials. That is, if the curl of the vector field f vanishes, then f can be written as, that is, del cross, if the curl of the vector field f vanishes, that is, if del cross f is equal to 0, then f can be written as the gradient of a scalar potential. We know the identity that curl of gradient of any scalar function, that is the gradient of the scalar function, the curl of gradient of the scalar function, that is equal to 0, then this f can be written as f is equal to minus del v, because here this minus sign is purely conventional. Minus sign is purely conventional, because conventional in the sense, suppose if this f can be electric field or magnetic field. If f is an electric field, then to calculate the electric field, usually we take the distance from the charge to that particular point, from the charge to that particular point. We are moving away from the charge. To calculate the potential, electric potential, we will take the reverse. That is, electric potential is defined as the work done to bring a charge from infinity to that point, work done in bringing a unit positive charge from infinity to that point against the electrostatic field. That is the definition of the electrostatic potential. Here we are bringing the charge towards the charge. That is why while calculating the electric potential, we are taking the minus sign, if f is the electric field vector. Okay. ഇപ്പോൾ കേൾ ഓഫ് എനി വെക്റ്റർ എഫ് 0 എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ നമുക്ക് ഇവിടെ എഴുതാൻ പറ്റാവുന്ന ഒരു ക്വാണ്ടിറ്റി എഫിനെ നമുക്ക് ഡെൽ വി എന്ന് എഴുതാൻ പറ്റും. കാരണം കേൾ ഓഫ് ഗ്രാഡിയന്റ് ഓഫ് എനി വെക്റ്റർ ഈസ് 0. Therefore, we have the if curl of f is equal to 0, then this is a curl-less or irrotational field. The conclusion of this theorem is the following. Okay, this theorem 1. You can write curl-less or irrotational field. നമ്മൾ ഇതിനെക്കുറിച്ചൊക്കെ ഒരുപാട് ഡിസ്കസ് ചെയ്തിട്ടുണ്ട്. അതുകൊണ്ടാണ് ഞാൻ കൂടുതൽ എക്സ്പ്ലനേഷനിലേക്ക് പോവാത്തത്. ഒരു കേൾലെസ് ആയിട്ടുള്ള ഇറോട്ടേഷണൽ ആയിട്ടുള്ള ഫീൽഡിൻ്റെ പ്രോപ്പർട്ടീസുകൾ എന്തൊക്കെയാണ്? കേൾലെസ് ആണെങ്കിൽ ഒന്നാമത്തെ പ്രോപ്പർട്ടീസ് ഡെൽ ക്രോസ് എഫ് ഈസ് ഈക്വൽ ടു 0. Curl of the vector f is equal to 0. For example, the electric field. The curl of a vector function f is equal to 0. Therefore, I can write the curl of divergence of scalar function is equal to 0. Therefore, this is nothing but our f. That is, this f can be written as negative gradient of the potential. Negative sign we have chosen purely it is a conventional. That is, therefore, the second property I can write is if f is a curlless, that is the curl is 0, that is irrotational field, then this f is the gradient of some scalar. Okay, that is f can be written as negative gradient of the potential. Fine. Now see, what is the third property? All these conditions are equivalent. Whatever I am listing here, A, B, C, D, E, all those conditions are equivalent. They are given the same meaning. If del cross f is equal to 0, del cross f is equal to 0, if I apply the Stokes theorem, that is del cross f dot dA is equal to Stokes theorem convert the surface into line integral. This will be f dot d dl, that is equal to 0 because del cross f is already 0. Which means if I have a line integral that is from A to B, f dot dl, this is path independent. F dot dl 0 means this line integral is path independent. നമ്മൾ ഇതും കുറേ ഡിസ്കസ് ചെയ്തിട്ടുണ്ട് ലൈൻ ഇൻ്റഗ്രലിൻ്റെ സെഷനിൽ. എഫ് ഡോട്ട് ഡി എൽ ഈസ് പാത്ത് ഇൻഡിപെൻഡൻറ്റ്. For any given endpoints. Okay. Now, what about the closed path? Suppose if we have a line integral like this one path, starting point is A, and again endpoint is same, that is A is equal to B. In such a case, the closed line integral f dot dl will be 0. Therefore, I am going to write here the fourth condition, closed line integral f dot dl, that is equal to 0 for any closed loop. Okay, these are the consequences of the curlless field, or these are the properties of the curlless field. These all conditions are equivalent conditions. Equivalent conditions. Okay. Now, here we have discussed if the curl of that vector function is 0, then it will be curlless, and these are the properties. Now, if the divergence of the vector field E vanishes everywhere, that is the second case. If the divergence of a vector field vanishes, that is if del divergence of f is equal to 0, then the vector function f can be written as or expressed as a curl of a vector potential. Because see, we know if the divergence of curl of a vector is always 0, then if I compare these two equations, this can be written as f. Therefore, this f can be written as curl of A. Karanam, the divergence of curl of a vector is 0. That is the main conclusion of this theorem. Let us say that is theorem 2. We can write as divergence-less or solenoidal fields. നമ്മൾ മുമ്പ് ഡിസ്കസ് ചെയ്ത പോലെ ഡെൽ ക്രോസ് എഫ് 0 ആയ കേസ് നമ്മൾ കേൾലെസ് ഫീൽഡ് ഇറോട്ടേഷണൽ ഫീൽഡ് എന്ന് പറഞ്ഞ പോലെ ഞാൻ വെക്ടർ ഫംഗ്ഷൻ്റെ ഡൈവേർജൻസ് 0 ആവുകയാണെങ്കിൽ എന്നത് നമ്മൾ ഡൈവേർജൻസ്ലെസ് അല്ലെങ്കിൽ സോളിനോയിഡൽ ഫീൽഡ് എന്ന് പറയും. ഇത് നമ്മൾ ഡിസ്കസ് ചെയ്തിട്ടുണ്ട്. എങ്കിൽ എന്തൊക്കെയാണ് അതിൻ്റെ പ്രോപ്പർട്ടീസ് നോക്കാം. ഒന്നാമത്തെ പ്രോപ്പർട്ടീസ്, ഡെൽ ഡോട്ട് എഫ് ഈസ് ഈക്വൽ ടു 0, divergence is 0. Then if you apply Gauss divergence theorem, that will be del dot f d tau, that is over the volume, or dv, is equal to surface integral f dot dA. If this is 0, of course this will also be 0. That is surface integral f dot dA will be 0. Then artham that is surface integral f dot dA is independent of the surface for any given boundary. അങ്ങനെ നമുക്ക് എഴുതാൻ പറ്റും. Okay, that is B. I can write f dot dA, the surface, is independent of surface for any given boundary line. Then if the divergence of a vector function is 0, this del dot f is equal to 0 means we know that divergence of curl of any vector is 0. Divergence of curl of any vector is 0. Therefore, as I mentioned earlier, this is f. That is, if divergence of a vector function is 0, then that vector function f can be written as curl of another vector. Okay, that is our C. If del dot f is equal to 0, then f is can be written as del cross A. Then fourth point that I want to write the continuation of this one. That is, this is very similar to the case where we discussed the fourth point. That is, f dot dl is 0 for any closed loop. That is, line integral is 0 for any closed loop. Similarly, here for any closed loop, the surface integral is 0. F dot d is equal to 0 for any closed surface. From these two theorems, theorem 1 and theorem 2 and theorem 1, that the vector field function f that is here the second point, B point, that can be written as sum of, that can be written as F is equal to minus del V plus the second theorem, that is F is equal to del cross A. That is the vector function F can be written as minus del V plus del cross A. Okay, fine. This is all about the Helmholtz theorem.